Okay, hello everyone, and welcome to the daily space for Friday, June 15, 2018. I am your host, Dr. Andres Plazas, and as always, we are going to bring you a roundup of today's news from space and astronomy. So let's get started. So today, I'm gonna start with a story about Dyson Spheres and dark energy. So I was looking at the archive the other day, the Astro PH. The other day mean this morning, and then I found a paper called "Life versus Dark Energy: How an Advanced Civilization Could Resist the Accelerating Expansion of the Universe." So this is a paper written by a scientist at Fermilab, Dan Hooper, the Fermi National Accelerator Laboratory close to Chicago, one of the laboratories of the Department of Energy. And in this paper, the author speculates about how an advanced civilization would respond to the challenge of living in a universe that is dominated by dark energy. So we have talked about this in the past that as space spans, stars and other objects fall beyond what we call the cosmic horizon. So that means that it's going to be impossible for them to ever again be observed or otherwise interact with. So within approximately 100 billion years, like that's a lot of time. Let's remember that the age of the universe is about 14 billion years, 13.7. So within approximately 100 billion years, all of the matter that is not gravitationally bound to the galaxies that make up what we call the local group of galaxies, all of that matter will become causally disconnected from the Milky Way. So, and it will fall beyond the limits of the cosmic horizon. So, well, so what's going to happen, right? So the author speculates that if you have a sufficiently advanced civilization that is determined to maximize its ability to utilize energy, he's saying that this civilization should expand throughout the universe, and it should attempt to secure as many stars as possible before they become permanent, before they just become inaccessible due to the expansion of the universe, in particular to the accelerated expansion of the universe. So he says, okay, to this end, they could build what we call Dyson Spheres. And what are Dyson Spheres? So you may have heard in the news about this, but there is this physicist called Freeman Dyson, a very smart physicist, and he speculated in the 60s that a sufficiently advanced civilization would be likely to build a structure around a star that is capable of collecting all or most of the light emitted by the star. And actually, well, a lot of these Dyson spheres, all this concept has been used a lot in science fiction, but at the same time, people have actually looked for signatures of these spheres, of this type of structure. So this paper is very speculative, as you guys can see, but I thought it was like a fun paper. So yeah, the authors say like, okay, I am making two assumptions here. Like the first one, that a highly advanced civilization will attempt to maximize its access to usable energy. And the second assumption is that our current understanding of dark energy and its impact on the future of the cosmic expansion of the universe is approximately correct. So, as I said before, we believe that about 70% of the contents of the universe is what we call dark energy. It's some unknown substance that has what we call negative pressure and is causing the universe to expand faster and faster with time. So this is what we call the accelerated expansion of the universe, but we don't know what that is. So then the author in this paper actually starts doing some calculations and integrals using reasonable assumptions about the distribution of energy in a star and about the how much energy and how much velocity would it require or would it take to bring one star to move it across the universe. Because this is what this paper is suggesting, that we just bring, before the stars go away, beyond the cosmic horizon, we just bring them close together to our local neighborhood or an advanced civilization. But then one of the findings that the author explains is like, he says that he finds that very high mass stars, they will often evolve before reaching their destination to a central civilization. So basically they will just die before, if you're fetching a star, the star is gonna die before you can bring it back home. And then on the other hand, if you have a star that has very low mass, it's just going to generate too little energy. So then he goes on in this calculation to find like the right zone, and he finds a range of masses of stars. And he says, okay, I believe that the stars that are about 20% or about the same size in mass, the same weight in mass as our sun, they will be the most attractive targets for such an effort. So that's one of the findings of his calculations. And one of the other findings of the paper, he says, okay, if you find a civilization that is doing this, it would be expected that this process would provide a number of potentially observable signatures. So this civilization could appear like in a region of about tens of millions of light years in radius. And then in this particular region, you would expect that the civilization has expanded and is trying to fetch the stars. And then you would see that most of the stars lighter than 2 solar masses or masses of our sun are surrounded with Dyson spheres. So you would expect like a lack of signatures from this type of stars because they're being covered by what we call Dyson spheres. And they said, furthermore, during the acceleration of these stars and transition towards the home civilization, towards the central civilization, such stars could be accompanied by visible signals resulting from the large quantities of energy involved in this propulsion. So, yeah, there's a lot of speculation in the paper, but some of the calculations that he does, they make sense. They're based on reasonable assumptions. And yes, I thought it was an interesting paper to talk about because probably last year we heard in the news that some scientists were thinking, they were looking at a star and then they were seeing like a lack of energy coming from that star. So a lot of people were speculating, could it be that another civilization actually built a Dyson sphere next to this star? In the end, they found out that it was a bunch of dust or something like that, so it wasn't a Dyson sphere, but it's very interesting to figure that out or to entertain that idea. Well, the second story that I want to talk about, it's about the simulations, cosmological simulations. I found this story in Quanta magazine, so let me see if I can get this simulation running. There you go. It's mesmerizing. So this story is about how we simulate the universe. So here we have talked about the standard model of cosmology and how we have a big picture, like with the theory of the Big Bang and then the standard model of cosmology. And the thing with astronomy and in particular with cosmology is that it's more of an observational science than an experimental science because first we only have one universe and we can only observe whatever we get from the skies, right? Could it be in electromagnetic radiation form or recently in gravitational waves form? But at the end we're so to speak stuck with what we get from the skies. So it's different. It would be great if we could go to a lab and make a mini universe and then control all the parameters that we want. But then people thought, okay, we have computers, so maybe we can do it. So that's a huge challenge. So the article that I'm going to talk about right now, so they start explaining that in the earliest, the cosmologists started to tackle this challenge in the earliest 2000s. And at first the simulations, like, they really failed in a spectacular way, like they would not reproduce what you would observe. But then, of course, as time goes by and then you have a better computational capability, and then the understanding of the universe improves. Then scientists started to apply the laws of physics. You start with a smooth field on the very, very largest scales of the universe, then you apply the laws of physics to that smooth field with the small perturbations, and then you just let it evolve, and then try to see how it reproduces the large scale structure of the universe that we observe today. And then with time, then the results of these simulations started to look more and more similar to what you observe. And the cool thing about these simulations is that when you code these simulations and you sit in front of your computer, you're assuming a certain amount of dark matter and a certain amount of dark energy. And then the cool thing is that you can say, what if we did not have any dark matter? And then you can run these types of simulations and then compare to observations. And it turns out that the hypothesis of dark matter has been favored by this type of simulations. But one of the things is, and this might sound a little bit weird, but when you do this type of simulations, you find out that it is easier just to use simulations that only have dark matter, because the simulations that have what we call the regular matter or the baryonic matter, the matter from which we are made of, and the stars and all the gas and all the stuff that we can see from electromagnetic radiation, when you include that, actually it is very challenging to include all the physics processes that are going on with this type of regular matter. So when you as I said, so when they started doing the simulations, they started doing like only dark matter simulations. They find out that the dark matter was founded in halos, like in almost spherical or ellipsoidal halos of dark matter. And then the idea was that when we added the gas and the regular matter, then you would be able to see the star and the galaxy formation. So, okay, that was the idea. We just until now, this is still an area of research. We haven't been able to create like a simulation that where you have the dark matter and then you add the regular matter. We haven't been able to create a simulation that gives you like a perfect galaxy, a spiral galaxy. We have come very close, and in different regimes, some simulations have more resolutions than others, some simulations have more particles, but I'm talking about running code on the best software computers in the world, like even for weeks or even months. So it's still a hard feature. So the article then continues discussing that the results of the computer simulations from dark matter only, they still have problems, right? Like one of the problems is that when you have a galaxy like the Milky Way, then the dark matter only simulation gives you a halo of dark matter, and then you find a lot of what you call dwarf galaxies that start orbiting that halo, that are satellites of that main galaxy. And the example in the Milky Way is are the Magellanic Clouds. There's small Magellanic Cloud and the large Magellanic Cloud. One of the big problems is what we call the missing satellites problem, is that the simulation with dark matter and with the standard cosmological model is telling you that there should be a lot of satellites of the Milky Way, whereas in reality we have only been able to observe just a handful, like even 10 or dozens or something like that. The situation has improved from the observational point of view, for example, with new surveys such as the Dark Energy Survey, in which this is a survey which I am part of, and 2 years ago we published a paper with this survey in which we found more dwarf satellite galaxies of the Milky Way, in this way alleviating a little bit the problem of the missing satellites problem, but it still didn't solve it completely. So the article concludes by pointing it out that nowadays people are starting to introduce the effects of baryonic matter, and in addition of having the dark matter only simulations, people are starting to put, for example, a supermassive black hole in the center of spiral galaxies, which we know they are there. So we're taking into account another process such as this, and then in addition we're putting other stuff such as supernovae. And what are these things doing? Like a black hole or a supernovae, they are actually perturbing the surrounding of a galaxy with, for example, a supernovae that creates an explosion, that creates like a bubble, and then you have a bunch of supernovae exploding next to each other. They create these super bubbles that in the end are going to clear off the gas in a particular region of a galaxy, and this is going to suppress the star formation of the galaxies. And then this is going to affect how the galaxy in the end looks like, because if you have a simulation that has only dark matter or a little bit of baryonic matter, then you're going to predict that galaxies should be producing more stars than what you actually observe. This is one of the observables that we have, the amount of stars that a galaxy produces. Yes, so let me put this simulation again. So I thought it was very interesting because this is on the one hand, we have these models, and it is an amazing feature to try to simulate the universe from the physics that we know, and it provides a lot of insight, because in the end, a lot of insight about the standard model of cosmology as we understand it. In the end, we want to compare what we get from the simulations to what we get from observations. But as I said, the simulations still have these problems. Some people claim, in summary, that by adding the effects of, for example, supernovae or black holes, which are effects of or baryonic matter, or like the ordinary matter, some people claim that by adding these effects of these types of physics, then you're going to be able to solve the problem. But then there are still people in the community that think, maybe there is no dark matter. Maybe we need to do a modification of the Newtonian dynamics, and maybe that's what's going on. So this is still a debate going on, and this is relevant because the third story that I wanted to tell you guys about today is related to this. So there was a press conference, and the title of the paper was, or the title of the press conference was, "No Need for Dark Matter to Explain Dynamics of Dwarf Galaxies." So you're going to see probably, maybe you've seen in the news, a lot of these claims like, oh, we don't need dark matter, or oh, actually we have confirmed dark matter. So just to be clear, the standard model of cosmology is called the lambda CDM model. That model calls for the existence of dark matter, and it favors that hypothesis. That doesn't mean that people aren't trying to come up with new ideas to try to figure out what dark matter is, first of all, or whether we need dark matter or not. So sometimes you're gonna find, oh, but I found in this galaxy that you actually don't need a lot of dark matter, so we don't need dark matter. But then maybe in a few months we're gonna find another paper by a group of scientists who do simulation, and then they're gonna say, oh, actually, yes, you can fit that observation that you did within the model of dark matter, and this is fine. This is how science works. Like, we're trying to test hypotheses, and in the end, as I have said many times, we need to resort to evidence. So the best thing that we need to do is to gather more data, which we are doing right now and we are planning to do. But just in summary, and to wrap up, this press release, there were astronomers from the Observatoire de Paris, is the observatory in Paris, and a Chinese group as well. They said that if you have a dwarf galaxy that's actually encountering the Milky Way from the first time, so you have the galaxy that is the galaxy formation, and you have a dwarf galaxy that is actually going and being trapped by the Milky Way and become a satellite of the Milky Way. Actually, what's happening is that the Milky Way has gravitational forces and tidal forces that could explain the movement of the stars within that particular satellite without having to invoke the hypothesis of dark matter. So the scientists showed that they found they made these calculations and these observations, and they said, if we assume that it is actually the Milky Way that is shaping the dynamics of this satellite galaxy, then we can explain the movements of the stars, the velocities of the stars within the satellite galaxies, what you call the velocity dispersion along the line of sight. The alternative hypothesis was that the Milky Way actually is not doing a lot of, it doesn't have a lot of influence of the satellite galaxy, and it is actually mainly the dark matter within that satellite galaxy that is governing the dynamics of the movement of the individual stars. And that velocity dispersion within the satellite galaxy could be explained by the gravity generated by dark matter. So that's the standard hypothesis, and then the alternative hypothesis that is shown in this study is that actually it is the Milky Way, the gravity of the Milky Way, that is causing the movement of these individual stars in the satellite galaxy. So, and in the end, the author said, like, well, this doesn't necessarily mean that there is absence of dark matter in dwarf galaxies, of course, but it is an important measurement that shows, like, do we actually need dark matter or not? Well, in the end, if you have a hypothesis, you should be this hypothesis should work for more than one observation. So I would expect that this hypothesis, that you assume that you don't have dark matter, and then you have this alternative hypothesis. This alternative hypothesis should be able to explain all range of observations that we have so far. And remember, the dark matter hypothesis actually has been successful in describing the formation, not only the formation of galaxies on the galaxy level, that not only the formation of objects in the universe on the galaxy level, but also the formation of the structures in the universe on the largest scales, on clusters of galaxies and of the cosmic web. And one of the main reasons we favor the dark matter hypothesis, even though we haven't seen it yet, we haven't found what dark matter is, one of the main reasons is the measurements from the cosmic microwave background, which is what we call an aftermath of the Big Bang. Is the radiation left over from the Big Bang, but you can actually make very precise, if you have the observations from the cosmic microwave background and you have your standard cosmological model that has dark matter, you can actually make very, very precise predictions about what you should observe, and those predictions, those observations actually match what the predictions are. So yeah, so that's what I wanted to tell you today. So maybe we can move over for questions or comments, and see what you guys think. Hello everyone. So let me go back. I always need to go back and see the comments. Hello everyone. Dyson sphere, not a swarm, a sphere. Okay. So I said some people are speculating what do I actually do. So I did my PhD in observational cosmology, actually, in what's called weak lensing within the dark energy survey. And I actually spent a lot of time looking at the detectors of the dark energy camera. That's a camera that it's in Chile. It's about a 500 megapixel camera, one of the largest digital cameras in the world. And they use charge coupled devices. And the scientific motivation that I was pursuing, that I'm still pursuing, is try to figure out what dark energy is from the observational point of view. So when I was in grad school, we used this technique called weak gravitational lensing. The other day I talked about gravitational lensing in general, but in particular there's something called weak gravitational lensing, in which a galaxy gets distorted by the large scale structure of the universe. The light of a galaxy gets a very tiny distortion, and it's called weak because you cannot tell it just by looking at it. You need millions and hundreds of millions of galaxies to figure it out. So the signal is very weak, but if we manage to measure it, then we can put a lot of constraints on what dark energy is or how it should behave. So a lot of the research goes into understanding the systematic errors that could go into your telescope, into your detectors, into the atmosphere. And most of my PhD was spent trying to understand how the detector is going to bias the shape measurement of a galaxy, for example. Stuff like that. Um, so there's somebody pointed out a paper on sterile neutrinos. I haven't read that paper in particular. That could be a candidate for dark energy. So I don't know a lot about the sterile neutrinos, but the other day I was visiting a colleague at Fermilab, which is not that far from where I am. And my colleague had the idea of putting a cube satellite with a detector to try to measure X-rays from a particular source and try to figure out if the signal from the particular source actually could be produced by dark matter, like sterile neutrinos, or sterile, I don't know how to say it. But anyhow, this is one of the candidates of dark matter, and I do know that there are certain observations from clusters in a certain particular part of the spectrum that has a peak that is not explained by the standard model of particle physics. And some people have suggested that a sterile neutrino could actually be causing this. So this is a type of neutrino that is not part of the standard model of particle physics. So yeah, that's all I know. Sorry for that, but I'm gonna take a look at the paper that Larry points out. But questions, Larry has so many questions. That's good. That's okay. I will do my best to try to answer them, or try to figure out where to answer them, because of course I don't know everything. What about your foodie strip? What do you mean by foodie strip? Like what I'm wearing, or like Peter asked this? Okay, that's one question. Okay, so before I talked about the shirt, so somebody, Uncle Bill, is asking us, does our dark matter halo stand beyond the Magellanic Clouds and other satellite galaxies? Yes, it does. And they actually, we believe that they're also dominated by dark matter. And this is what we believe is happening. So you can imagine of like a large halo surrounding the Milky Way. And then inside you can find these satellite galaxies that have the little orange halos. And I'm oversimplifying this because people thought, well, people, of course, you start with the spherical car, right? So you start with a sphere, and then you start making an ellipsoid, and then you find out that it's more complicated than that. But the model, as I was explaining in the second story, the model tells us that there should be more satellite galaxies than that we see. And then the missing satellite problems is that we don't see those as many dwarf galaxies as we should see. So that's one thing. And then related to the third story that I was talking about, people are saying like, oh, actually, maybe we don't need the hypothesis of dark matter in satellite galaxies. That doesn't mean they don't have dark matter. Maybe they don't have as much dark matter as we thought they had. Maybe there's something else we're missing. Maybe these objects are not in equilibrium in such a way that they're still interacting with the tidal gravitational field, the tidal effects of the Milky Way, and that's why we see the motions that we see. So the shirt was about the World Cup. I'm wearing the jersey of the national team of my country, Colombia. I was born in Colombia, and I'm very excited because the World Cup started in Russia yesterday. So that's why I'm wearing the shirt. Okay. There you go, Colombia with an O, Colombia. So there is one more question. It says, I know the listed distance for the Andromeda galaxy from us is about 2.5 million light years away. We see the light as it was 2.5 million years ago. So it likely has moved since then. Does our measurement in distance account for the distance possibly covered in moving towards us? If so, how is it done? Um, I think it does take into account the peculiar movement of the galaxy. It's called the peculiar movement, the movement of the galaxy. Um, I don't know the rate in kilometers per second or any distance per unit of time. I don't know the actual rate at which it's moving, but the way it's usually done is by calculating. You take the spectra of the collective spectra of the galaxy, or you can measure, and then you see how it is redshifted or blue shifted actually. So most of the galaxies that we observed, we find that their spectra is shifted towards the red, and that's evidence in favor of the expansion of the universe. That's one of the observational uh, evidences for the expansion of the universe. The exception, for example, being Andromeda, that actually is blue shifted, and that's how we know that it's moving towards us. So I would think that the rate is not actually that high in such a way that it has made a lot of a difference to account for the time that has come between when it was 2.5 million light years, 2.5 million years, and now. So I'm not particularly sure, but what I am sure is that they do it with the spectroscopy. Another way that you can do is you can measure the Cepheids, and this is what Henrietta Leavitt did, the Harvard women, like 100 years ago, that calculated by hand all the movement of stars. One of them was Henrietta Leavitt, and discovered the stars that change their period and their luminosity change, and that's how we know we can, by knowing how the luminosity of these particular types of stars change, then we can figure out also how far away they are. And actually, that's how Hubble found out that Andromeda was outside of our galaxy, not in our galaxy. Back in the time of Hubble, in the 1920s, people were debating. We thought that the Milky Way was the only galaxy, like it was called like the island, like a universe. And then Hubble found these particular types of stars. He found them in Andromeda, and then he was able to determine the distance to Andromeda, and it was like a lot. So he found out that completely changed our view of the universe. Like, okay, there are more what they called back in the time island universes. So they were called computers, yeah, back in the time. Yes, in quotes. I mean, wanted to make it. Um, Computationally, is there a plethora of methods to make a cosmic simulation possible today rather than one key simplification? Yes, there are a lot of methods because there are a lot of parameters that you need to. First, there are the parameters from your cosmological model, their physical parameters, your parameters from your cosmological model. Then you have your physical parameters, and then you can choose what the focus of your simulation is going to be from the point of view of those parameters. But in addition to those set of parameters, you also have the parameters to make the simulation run. So what do I mean by that? How many particles are you going to simulate? What is going to be the size of your universe? So if you have a box that is huge, 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 and then you have to sacrifice what we call the resolutions, which is the distance between the smallest particle, the two smallest particles that of your simulation. And then for that, depending on what you want to do, then there are different techniques, and you can optimize the simulation in such a way that it gives you a faster result within one regime, and then it gives you a better result within another regime. In a perfect world, we will have infinite computational capacity, and then we will have like the gigantic box with a very small resolution, like a spatial resolution. But nowadays, that's still very computationally is very expensive. despite that, we have been able to produce amazing simulations, such as the Millennium simulation. If you go to YouTube and Google Cosmic Web or Millennium simulation or stuff like that, you're gonna see pretty cool stuff of how the universe forms with cosmic time. And then you can see in the end the cosmic web forming due to gravitational instability. Um, okay, guys, I think there are a couple of other questions, but I think I need to go because there is another stream after us. I think we're gonna have Dr. Matthew Richardson after us, but I'm very happy that you guys asked very interesting questions and even asked about what I was wearing and stuff like that. But okay, so I think we're gonna leave it like that for today. So thank you very much again for watching. This has been the Daily Space. This is a production of CosmoQuest. It is created by the Astronomical Society of the Pacific. So give us a follow, please, or consider subscribing. This will help us a lot. Next up on this channel will be Dr. Matthew Richardson. And so stay tuned. And the Daily Space will be back next week and every weekday at 1 p.m. Eastern, 10 a.m. Pacific time, and 6 p.m. London time. And you will have Dr. Pamela Gay back. So, all right. Bye bye, everyone.